This is a recording of a presentation that I gave in late October at the GSA Connects 2025 meeting in San Antonio, Texas, USA. It was an invited presentation that formed part of the Farouk El-Baz Award for Desert Research. It was given as a 30-minute presentation in the Advances in Fluvial Processes and Sediment Transport session, and other than this preamble, has been amended only very slightly. At the start, I would like to say thanks to Farouk El-Baz for the inspiration and initial endowment for the award all those years ago, and to the Quaternary Geology and Geomorphology division for administering the award. I would like to say thanks to Gerald Nansen, Bob Craddock, and other supporters for their efforts in putting the nomination together and for providing the citation that was read out at the awards ceremony. And finally, I would like to say thanks to the awards committee for deciding that I was worthy of being the 28th recipient of the award. I would also like to say it's a daunting task to summarise 30 plus years of desert river research, and the last 25 years in particular, in about 30 minutes, but I'm happy to take on this task. At the outset, I will also say that the award has lifted my spirits greatly. It's been a very tough year for me, both personally and professionally, and I don't need to go into full details, but I would just like to note the passing of two influential people. Firstly, my colleague Andrew Thomas, who finally lost his 3-year battle with pancreatic cancer in April. I had the good fortune to work with Andrew in the Kalahari Desert in Botswana and the Menegros Desert in Spain, and most of what I know about soil science can be attributed to him. And I'll come back to that briefly later. And also my dad, who passed away on his 87th birthday in June. A deep thinker, someone who never stopped inquiring and learning, and his approach has almost undoubtedly shaped my natural curiosity and scholarly approaches. One of the highlights of my life, and I think his, was taking my dad and my mum on a 10-day tour of the amazing desert landscapes of the American Southwest back in 2011 and acting as their landscape guide. In memoriam. I should also mention the support of my family. Here is one of my favourite photos, my wife Maggie and our then 3-year-old son walking deep in the Patagonian desert. To me, this picture highlights the beauty of desert landscapes, but also makes me think of young people walking away from their past and into their future. And I'll come back to this theme of past, present, future, retrospective, perspective, prospective, in various ways as I go along. But how did all this come about? How did I get interested in deserts, and desert rivers especially? I did an undergraduate geography degree at the University of Southampton, England, where we did a lot of stuff on very wet rivers, paleo-environmental reconstruction from very wet peat bogs, lots of stuff on very cold and very wet Arctic and alpine environments, but little to nothing on deserts. My first exposure to a desert came during post-graduation backpacking travels in India, excuse me, on camel through part of the Thar Desert in Rajasthan, near to the ancient city of Jaisalmer. To cut a very long story short, I then got a PhD scholarship at the University of Wollongong in Australia, working with Gerald Nansen with the incredibly loose idea of doing something on desert rivers. Chapter 1 of my PhD thesis eventually turned into a paper that I submitted while doing postdoctoral research at the University of the Witwatersrand in South Africa. Here's the reply from the associate editor that says something like, although both reviewers consider this to be a grade 1 paper, I feel that the paper requires some modifications to make it more substantially interesting. Well, I did what was required, and eventually the paper was published in Earth Science Reviews in the year 2000, around the time I started at the University of Wales, Aberystwyth, as it was then called. This paper is by far and away my best cited paper, and likely forever will be, so I thought I would use this opportunity to do a 25-year retrospective. So here's what's coming in the rest of the talk. I'm going to start with an overview of dryland river characteristics. I'll explain sections 3, addressing deficiencies in dryland fluvial research, and section 4, future dynamics and the management implications when I get to them. I'll then touch briefly on the interface between dryland fluvial geomorphology and other subdisciplines with a few slides, each of which really could be the subject of multiple other 30-minute talks. and then I'll briefly contemplate where we might be going next. Essentially, what have I, and we more generally, learnt over the last quarter of a century? What has, and what hasn't changed? And, if I'm lucky enough to be able to stick around, what might change over the next 25 years, especially in terms of dryland river research? So, what are the characteristics of a dryland river? If I were giving this talk to undergraduates, I'd give 5 minutes for them to turn around, speak to their neighbour and scribble down some thoughts. In this format, there isn't the opportunity to do that, but I bet if you were asked, many of you would at least list some of the following characteristics. The dryland rivers are characterised by long periods of no flow and by short-lived localised flood events. Many of them, I suspect you would say, are wide, sandy, gravelly channels, subject to episodic sediment transport, and that vegetation is sparse or non-existent, and that large floods typically lead to major channel changes so that the channels are in a state of almost permanent non-equilibrium. Now this image, taken out of a plane window on a flight into Cairo, encapsulates many of those characteristics. No flow, sparse vegetation, unstable, sandy and gravelly braided channels. This could also be a view of some of the rivers of the USA southwest, or parts of the Middle East, or perhaps parts of Africa, such as Namibia. So, clearly, some dryland rivers do have those characteristics. But at the start of my PhD, as I started reading and compiling the available literature, I quickly realised that this reflected an obvious geographical bias in research. Presenting these characteristics as typical of all dryland rivers reflected a tendency for research at that time to have focused on relatively small, steep catchments, particularly in the southwest USA or the Middle East, and larger, lower gradient rivers in tectonically inactive settings remained relatively poorly researched. So what about the amazing features of Cooper Creek in Australia's Channel Country? The extensive fine-grained anastomosing channel complexes with floods that expand up to about 60 kilometres wide and lead to all kinds of weird and wonderful interactions between the channels and the floodplains. These kinds of features had been documented and explained by Gerald Nansen and colleagues in the 1980s and early 1990s, but had not made it into textbook descriptions of desert river characteristics. But the very existence of such rivers on such an epic scale threw into question many of the generalisations about desert rivers. For example, in these sorts of dryland rivers with their low stream powers and floods that take 3 to 4 months to travel through hundreds of kilometres of channels, and channels that are barely changed over many decades, are these really non-equilibrium systems? Anyway, a few months after arriving in Wollongong and reading what I could about work on dryland rivers in central and northern Australia, the early work of George Williams, the work of Jeff Pickup, Vic Baker, Peter Patton and so on, it was off to the dead centre of Australia. This is a nice image of the Australian continent, but far too green to really reflect the widespread and semi-arid landscapes that predominate. Gerald and I met with Jeff Pickup, who at that time was working mainly on using remote sensing to document the highly degraded lands around the McDonald Ranges near Alice Springs, and we took the old-style 1 to 250,000 topographic maps and first-generation handheld GPS devices and followed some of the larger rivers away from the central ranges and out onto the northern plains. A vast, largely sandy expanse with rivers that, in theory at least, flow north and north-eastwards and east towards the Simpson Desert on the margins of the Lake Eyre Depot Centre. In the headwaters of these rivers there were no great surprises. Perhaps more bankline vegetation than you might expect on a typical desert or dryland river, but otherwise low sinuosity, wide and sandy gravelly channels predominated. In fact, these channels were not so different to many a creek, wash, draw, wadi, barranco, or nahal elsewhere in the world. But as you emerged out onto the Piedmont and traced down through the middle to lower reaches of many rivers, it all changed. On many rivers we found widespread, extensive anabranching channel complexes, many hundreds of metres across, with 10, 12, maybe 15 channels dividing and rejoining around vegetated ridges and islands. Nothing like the textbooks described. So what was going on? We worked out that much was down to the role of lower magnitude flows coming down small tributaries. Here's a section of the Sandover-Bundy River, several hundreds of kilometres out from the central ranges. And when it flows, the flows run from left to right. Large flows generated by frontal rainfall in the headwaters might reach here once every 3 to 4 years. But small, localised flows, likely generated by convective thunderstorms in the headwaters of the smaller catchments, and you can just see two small tributaries joining the river from the north. These tributaries and the short sections of channel downstream of them might flow more frequently, perhaps every 1 to 2 years. And we concluded that the small amounts of water coming down the tributaries stimulated the growth of in-channel trees, principally river red gums, Eucalyptus camaldulensis, and in some reaches the inland tea tree, Melaleuca glomerata. So if we enlarge this portion of the channel here, you can see how the density of trees increases downstream of the tributary junctions. Now the key point is that once established, these trees can withstand the rarer, larger floods that come down the channel from the headwaters, and they provide obstacles to flow, so initiating lee-side deposits of sand and gravel. On image 3 there, the red circle indicates a person seated in the shade, showing that these deposits and the protections offered by the parent trees provided a nursery for germination of seedlings, which in turn grew into saplings and eventually mature trees, and which also initiate deposition. The end result is that larger ridges or islands supporting mature trees end up separating multiple channels relatively free of trees. In some cases, ridges can grow up to 2 to 3 metres tall. We published these findings up, including a sketch explaining how an initially chaotic arrangement of trees on a channel bed over time becomes organised into a series of parallel channels, ridges and islands that facilitate onwards flow and sediment transport. These are stable, long-lived channels, ridges and islands that are finely adjusted to the prevailing flow and sediment transport conditions. In fact, they represent archetypal equilibrium channel floodplain forms. But in the lower reaches of many rivers, it was a different story. The periodic large floods were not regular enough and certainly did not have enough power to sustain well-defined channels, and many decreased dramatically in width downstream, sometimes with multiple splay channels and distributaries diverging, and eventually terminated in what are widely referred to in Australia as floodouts. This is the example of the Sandover River floodout here. The occasional large flows spill beyond the terminus of the channel across the low gradient, low relief channelless floodplains, but, bizarrely, in some cases the rare flows would coalesce back into what I termed reforming channels, which would then continue on their merry way, at least for some distance. We also published these findings up in a series of papers that also documented the sedimentology and some of the late Quaternary history of these dryland fluvial landscapes. So even by the end of the first field season, it was clear that we were developing a new understanding of dryland river form, processes and change, new terminologies, new conceptual models that could challenge the established textbook notions of the typical characteristics of dryland rivers. So on the basis of the emerging evidence from Central Australia and my continued reading of the desert textbooks and the journal literature, in 2000 I published my global overview. There's around 350 references in that paper, which I'm confident captured roughly 90 to 95% of the peer-reviewed literature at the time. The abstract highlighted how findings emerging from places like Central Australia were demonstrating much greater diversity in dryland river process, form and change than had hitherto been appreciated, and I hope, from what I've said so far, I have convinced you of that point. But my review also pinpointed areas of deficiency in dryland fluvial geomorphological research, including the limited study of some aspect of modern dryland rivers, the limited understanding of dryland river behaviour over longer timescales, and the lack of integration between the results from short-term process form studies and studies of the longer-term histories of river behaviour. In addition, I suggested that linking knowledge of past hydrological and channel changes to present-day dryland river changes should be a key research priority. I argued that such research was a way to provide a sound theoretical basis for the assessment of future developments in dryland rivers and would thereby contribute both to improved scientific understanding and to environmentally sensitive management. So we've covered the fluvial diversity aspect. In the next two parts of the talk, I'm going to cover the other two issues here. To do so, I'm going to focus almost exclusively on work that I've done with others. This is certainly not, and I must stress this is certainly not to dismiss or denigrate the dryland rivers work of other individuals or teams, but obviously my work is what I know best and what I feel best able to comment on. So since the Australia days, I've done much research and travel in deserts and drylands worldwide. First, a lot of travel in southern Africa, including the Kalahari, Karoo and Namib deserts. Then work in parts of the arid and semi-arid Mediterranean, Crete and Spain especially. I've ventured into the North American deserts, including those on Hawaii. Yes, Hawaii has a desert, the Kau Desert, a chemical desert on the downwind side of the Kilauea volcano. And I've done increasing amounts of travel and work in the deserts and drylands of South America and India in recent years. I've also worked on satellite imagery and data sets acquired by others from the Bolivian Altiplano, the Sahara and inland China, and I've travelled through parts of East Africa, Jordan and more dryland parts of the northwest United States, particularly the drier parts of Washington and Oregon states. One thing I quickly got very interested in when I went to Africa was bedrock and mixed bedrock alluvial dryland rivers. Now, Alan Wall and others had really helped pull together the literature on bedrock rivers in general in the 1990s. The top image there is of the Bungle Ranges in northwest Australia, a site which Alan had worked at, and many others had looked at dryland canyons as potential sites for slackwater flood deposits. But in southern Africa particularly, the widespread presence of dryland rivers with potholes, waterfalls and canyons and or extensive anabranching patterns had gone largely unnoticed and certainly had not been well documented. So we started to change that, including by documenting how large rivers such as the Middle Orange River alternated along their length from extensive lower gradient dominantly alluvial sections with a few channels and large islands to steeper gradient dominantly bedrock sections where multiple channels picked out lines of weakness created by joints, fractures and foliation in metamorphic and igneous lithologies. We also documented and explained the geological controls on abrupt channel pattern transitions and large floodplain wetland complexes in the semi-arid and dry subhumid parts of northeast South Africa. We developed conceptual models to show how following Gondwana breakup, rivers have superimposed themselves onto the succession of Karoo supergroup lithologies, and the highly resistant intrusive dolerite sills and dikes commonly served as stable base levels for upstream reaches underlain by more erodible sedimentary rocks. The ensuing lateral migration and valley widening over time creates the accommodation space for the floodplain wetlands, at least for a while, until the sill or dike is eventually breached by river incision and large-scale nick points work upstream, dropping the base level, initiating large gullies and consuming the floodplain wetlands. So we had geologically controlled cycles of floodplain wetland formation and destruction. And then we come to the Okavango Delta, the world's 1000th World Heritage Site, and another example of a geologically controlled wetland in a dryland, this one located in the northern Kalahari Desert. This work was started by Spike McCarthy and colleagues in the 1980s, but we made additional contributions during my postdoctoral work. Essentially, we've outlined how a combination of water, sand and biotic activity, most notably the activity of hippopotami, leads to various channel dynamics and the formation of a range of floodplain wetland features, such as the highly unusual saline islands shown in the middle image on the bottom there. By the early 2000s, we were confident enough that we'd identified enough new fluvial forms and processes to write a paper specifically about wetlands and drylands, and we've developed that since. Wetlands and drylands globally go by a whole range of weird and wonderful local and regional names: billabongs, boffidalis, bogs, boinkers, cienagas, and so on. And they come in all sorts of shapes and sizes. Even in the most arid parts of the world, such as the Atacama Desert, you can find small wetlands sustained by local groundwater seepage. Now, interestingly, most moderate to large wetlands and drylands are associated with rivers, but with the exception of the early work in the Okavango Delta, these did not feature in my 2000 review paper because there was very little in the peer-reviewed literature at the time. So again, new understandings of dryland river forms, processes and change, new terminologies, new conceptual models, all of which were challenging the textbook notions of the typical characteristics of dryland rivers. What about the second main area of deficiency, the limited understanding of dryland river behaviour over longer timescales? At the time of my review, robust chronologies were lacking for many dryland rivers. Flood records based on slackwater sediments were being built up in many parts of the world, and some good thermoluminescence work was done in Australia to tease out longer-term channel floodplain changes. But by the late 1990s, optically stimulated luminescence dating was all the rage. Yet there were relatively few studies in dryland contexts. So with luminescence dating specialists, colleagues at Aberystwyth, most notably Jeff Duller and our students, but also specialists at some other laboratories worldwide, I set about developing geomorphically informed sampling approaches to establish dates and rates for various aspects of dryland river form, process and change. I won't go into details in this presentation, but just to note that we've successfully dated scroll bar sequences to work out lateral migration rates of meander bends. We've successfully dated the downstream growth of anabranches, in this case along Magilla Creek in northern Australia as it progrades into Majimbadi Billabong. Essentially, in this setting, we showed how an initially chaotic pattern of trees and sand can develop into an organised system of relatively tree-free channels and intervening ridges and islands in a few thousand years. We have dated coarse-grained fluvial terraces to work out histories of cut and fill in high-relief catchments in Crete. And we have dated floodplain successions now exposed by river incision in places like South Africa, slowly accreting stacked paleosols that over the last 40,000 years or so have gradually acquired coloration and other climatically diagnostic pedogenic features reflective of changing environmental conditions. And in some situations, we've been able to take quite a sophisticated quantitative approach to reconstructing channel process, form and change. Here's the example of the Okavango Delta, where there is a vast array of paleochannels, but none of which had been dated until recently. We focused on the Kugana region of the delta, shown in the inset image in the top right of the slide there. And the main image is a blow-up of that region, where one can see a suite of large sinuous paleochannels, most of which are significantly larger than the laterally stable modern-day channels marked in the solid black. Here we dated a series of scroll bar sequences and channel infills, with most of the ages clustering between about 8,000 to 4,000 years ago. This seemed to imply significantly enhanced mid-Holocene activity in this wetland in a dryland. Can we quantify this enhanced activity? Yes, we can. Our earlier work had established the modern-day processes and hydraulic geometry of these channels very well. In this setting, the permeable, reed and sedge-lined banks of these channels mean that most downstream increases or decreases in discharge are accommodated by increases or decreases in width, rather than by mutual co-adjustments of width, depth and velocity. This enables us to use cautious extrapolation of these relationships to establish the paleo-discharge of the former larger channels. So with 120 to 150 metre wide paleo channels, we could work out that the paleo discharges in the former larger channels were 9 to 10 times the discharges of the modern channels at an equivalent point in the delta. But interestingly enough, on these low gradients, even though the discharges were substantially higher, the unit stream powers in the paleo channels were only a little bit higher, roughly double what they are at present. Nonetheless, even these relatively small stream power changes have been enough to trigger major morphological changes. Threshold crossing changes, in fact, from large laterally migrating paleo channels to the much smaller, stable, modern channels. In the Okavango, the enhanced discharges resulted from southwards movement of the African tropical rain belt, which is associated in some complex way with the seasonal dynamics of the intertropical convergence zone. Today, as shown in the lower left image there, the intertropical convergence zone moves back and forth seasonally, but only just impinges on the very headwaters of the Okavango catchment. But in the early to mid-Holocene, it must have come substantially farther south in the austral summer for extended periods of time to generate the much larger and more reliable discharges that supported the former larger, more laterally active paleochannels. Then, in the late Holocene, the northwards retreat of the average annual position of the ITCZ and rain belt led to the channels contracting in size once again. Note, however, that both the paleo channels and the modern channel forms are quasi-equilibrium forms that were or are currently adjusted to the prevailing boundary conditions. Interestingly, we're starting to pick up similar patterns on other dryland rivers worldwide, most notably the Warrego River in Australia, where large laterally migrating paleo channels that were active 8,000 to 4,000 years ago have transformed in recent millennia to much smaller, laterally stable, anabranching channel complexes. This is work that was done with Tim Ralph as part of Zach Larkin's PhD thesis. Here too, we can quantify that change in terms of discharge and stream powers. And then with these sorts of data sets, we can address the other research deficiencies and priorities that I'd identified all those years ago. Namely, placing present-day forms and processes and short-term behaviour in longer-term context to look to the future. One thing we can do is look more critically at the language of river dynamics. Following Kirsty Fryers and Gary Briley, we can distinguish between river behaviour and river change. So, for instance, river behaviour is adjustment within boundary conditions. Change is more profound transformation arising from changing boundary conditions, whether that be through natural or anthropogenic forced changes. We can also critically address concepts which were not around in the year 2000 when I did my review, but are now quite trendy, such as resilience. So, for instance, by most definitions, the adjustments on the Okavango and Warrego rivers in the early to mid-Holocene and then through to the late Holocene represent a step change to lower resilience. And it might be thought that with current climate projections and various anthropogenic impacts, that the future may bring yet another step change to even lower levels of resilience. But is this necessarily the case for all dryland rivers? Let's take the example of the North and South Platte rivers in the Midwest USA. Flow regulation and irrigation agriculture have fundamentally transformed the geomorphology of reaches of these rivers from a shifting network of sandy braided channels and temporary islands to complexes of anabranching channels and more stable vegetated islands. Could this be considered to represent greater geomorphological resilience in the sense that banks and islands are now more stable? But at what costs to ecological resilience? These river changes have had profound impacts on riparian ecosystems, with many native species such as cottonwoods outcompeted by exotic species, and loss of the roosting and nesting habitats for rare and endangered species such as the sandhill crane. In my more optimistic moments, which are few and far between, perhaps we can look forward to a future where there is a halfway house, with properly implemented ecological flow releases taken seriously and implemented for maintenance of geomorphological and ecological diversity, and so maintain a degree of resilience. But as I say, my optimistic moments are few and far between. In the Australian context, we've looked more closely at potential future channel dynamics under climate change scenarios, and even under relatively conservative projections, it's a worrying trend. Many Australian rivers may be pushed along a spectrum from sinuous, through-going rivers towards downstream declining rivers that start to anabranch and lose form in the lower reaches, some of which may eventually break down and terminate in floodouts. By 2070, it's not exactly that rivers will be unrecognisable, as the headline writers for our popular article insisted on saying, but certainly there is high potential for transformative threshold crossing changes on many rivers. To start concluding, I just want to very quickly illustrate how dryland river research can dovetail productively with other aspects of dryland or desert science. This includes aeolian and extraterrestrial geomorphology. I've had some amazing trips with Bob Craddock and colleagues from the Smithsonian Institution to all sorts of places, looking at fluvial reworking of tephra and flood-out development in Hawaii's Kau Desert, aeolian fluvial interactions in Australia's Simpson Desert, and the processes leading to formation of amphitheatre-headed valleys in places like the Colorado Plateau and the Chilean Atacama Desert. These sorts of places act as analogues for certain surface processes on Mars and other planetary bodies like Titan. I come back to work with Andrew Thomas and our Chinese postdoctoral student, Xubin Lan, work that combines fluvial process understanding, geochronology, and soil chemistry and soil microbial insights to look at the potential for carbon storage and reworking in places like the Chobe River in Botswana. This is unpublished work, but if accepted, will add to Andrew's legacy, particularly in terms of looking at these wetlands and drylands as carbon storage hotspots. Understanding of dryland river process, form and change can also be applied in many archaeological contexts, such as the Kalambo Basin on the border of Zambia and Tanzania, where we've successfully established conceptual models to help explain preservation and visibility of archaeological sequences, and used thermally transferred, optically stimulated luminescence dating to push back chronologies of human tool-making activities to more than 300,000 years. And we've applied similar understandings of dryland rivers in various river and wetland management, conservation and restoration contexts, particularly in places like South Africa. So, the future is bright for fluvial geomorphology in drylands. Or is it? With a few exceptions, in this talk, I've tended to focus on the more pristine dryland river environments. But worldwide, many dryland rivers are under direct or indirect threat from a whole variety of human activities. While the effects of global climate change are being seen in more and more devastating flash floods that put larger and larger numbers of people at risk, as we have seen with devastating consequences in the San Antonio region in just the last few months. So I do feel that we're at a critical juncture. What is the future? I've had a lot of fun along the way swinging, digging and hammering in various global locations. I've worked hard, I've made a lot of sacrifices, but taken advantage of all opportunities, and I've also been very lucky with my mentoring and the vast majority of my collaborations. But besides research, I've invested a lot of time in my teaching and increasingly in a diverse range of education and outreach activities, including production of a series of colour booklets. The flash flood example is shown here. And we've also made infographics to translate some of these findings into other languages. The example there is in Arabic. I intend to stick around for a while longer, but I need to start handing more onto the next generation of researchers. So in the spirit of the El-Baz Award, which encourages younger researchers to strive for excellence in desert research, I'm going to end with a few thoughts. One key thought is that alongside the research, we need to encourage non-specialist engagement with dryland rivers. We need to raise awareness of the importance, uniqueness, and, yes, the beauty and fragility of these environments and their wider landscapes. Over recent years, with technologically more savvy colleagues, I've been trialling various forms of engagement with a diverse suite of audiences through various social media and art science activities, including producing videos of flash floods in this instant in the Patagonian desert to help bring the desert landscape into people's lives in ways not previously possible. I've dabbled with various forms of poetry, acrostics, nonnets and haikus. We've made social media short videos to explain different desert landscapes and desert features. And we've made links to a whole variety of world days like World Wetlands Day, World Rivers Day, and others, including International Geodiversity Day. And I've worked with others that have been using scientific imagery to make visually appealing what you might call geoart that might also stimulate questions about dryland river form, process and change. There are also some wonderful documentary films out there that examine dryland rivers in their social, geo-ecological, political context. This one on lower right there is called A River Out of Time. It's based around the Colorado river system and is freely available online. Visual art that can help tell stories is also really important. This poster is from a recent project looking at water security in the Patagonian desert. The Chubut River is represented here, flowing from its source in the Andes through to the arid east coast, and the tributaries represent inputs to the shaping of the modern catchment and its water management, including the indigenous peoples, pueblos originarios, and the arrival of the Welsh settlers, the fledgling Argentine government's conquest of the desert, and the various voices that today contribute to debates about the future of the river, including the marginalised voices of indigenous women in particular. We've done these sorts of outputs not only in English, but also in Welsh and Spanish, to tap different local communities and encourage as inclusive a discussion as possible. Essentially, we need to raise awareness about dryland rivers, provoke a sense of wonder and enchantment about dryland rivers, but also grow and nurture a culture of care for dryland rivers. If people don't care about dryland rivers and their wider landscapes, at best they will be seen negatively and dismissed, as this series of postcards illustrates, and at worst they will be irreversibly damaged or lost. So I'll leave you with this panorama of one of my favourite desert river landscapes, the Orange River Gorge in Okrabi's Falls National Park in western South Africa. It's a beautiful place for sure, but I would argue even more beautiful if you contemplate many of the still unanswered aspects of its geomorphology. How fast is the waterfall at the head of the channel retreating? And how old is the gorge? What role do the occasional floods play in this rate of retreat? What are the rates of gorge deepening and widening through river incision and rockfall? What controls the spacing of pools and boulder riffles along the gorge floor? What is happening to the complex of anabranches above the falls as the waterfall retreats? We need to work on communicating these sorts of questions and ideally answers in accessible ways to diverse audiences so that people feel engaged and compelled to care. So, 3 big words to end: geoeducation, geotourism, geoheritage. It's over to the younger generation of dryland researchers, particularly, but not exclusively. It's a job for all of us. I'll end here. Many thanks again for listening.